Can you hear me? Can you see my web page on PowerPoint slides, chapter 5? Okay, I say, Michaela, send a chat that she can hear me. I'm going to start the class for today and going to go over the rest of the chapter 5 question. Okay. All right. We go now states of matter, gas pressure measurements, and the behavior of gases in terms of gas laws, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. Today I am going to talk more about ideal gas law. That's what we're going to do today. Then I'm going to talk about Dalton's law of partial pressure. This law, Dalton's law of partial pressure, is used to get the total pressure of a gas mixture based on partial pressures of the component gases. I will show you how we could do it. Then we are going to talk about kinetic molecular theory of gases, liquids, and solids. There are 3 types of intermolecular forces that are present in gaseous particles, among liquids, among solids. I'm going to talk about them and introduce to the intermolecular forces. Then we're going to look at behavior of liquid at molecular level and describe the properties of liquids at molecular level. All right. This is where I stopped last time. We talk about the standard temperature and pressure based on Gay-Lussac's law, Avogadro's law. Avogadro's law is the main law that describes STP. According to the Avogadro's law, volume of a gas is directly proportional to the number of moles. Therefore, Avogadro's law gives volume of certain number of moles or molecules. If you have a gas sample, 2 gas samples at certain temperature and pressure, or standard temperature and pressure, they contain the same number of moles or molecules in that same number of volume. A mole is, we already talked about it, a mole is Avogadro number of particles of anything. We defined the mole in last chapter. A volume of a gas at STP contains Avogadro number of molecules. So 1 mole of a gas at STP occupies 22.4 liters based on calculations using the Avogadro's law. This amount, 1 mole of any gas at STP, 22.4 liters, is called molar volume of 1 mole of gas at molar volume is 22.4 liters. So let's look at some problems about Avogadro's law. A student has 3 samples of gases that have equal volume. Avogadro's law deal with equal volumes and number of moles. The 3 gases are oxygen, O2, carbon dioxide, CO2, ammonia, NH3. All these 3 gases are at the same temperature. Which of the following sample contains the largest number of molecules? First one says oxygen contains largest number of molecules. When you have 1 mole of 3 samples with equal volume at same temperature and pressure, they must contain same number of moles. Therefore, if it contains same number of oxygen, carbon dioxide, and ammonia, they also eventually moles converted to molecules, same number of molecules of oxygen, carbon dioxide, and ammonia. Therefore, these 3 statements are not true. And the last choice given is all 3 gas sample contains an equal number of molecules. All these 3 gases contain same number of moles, therefore same number of molecules. That is the correct answer. That's based on the idea at same temperature and pressure, 1 mole of gas has volume of 22.4, same volume. A student has 3 gas samples, same 3 gas samples. They are at the same temperature and pressure. Which of the following sample contains largest number of atoms? Now, this is kind of different from the problem we are talking about. This is different from problem 59. Their largest number of atoms. They all contain same number of molecules. But oxygen has 2 atoms. There are two oxygen atoms. Carbon dioxide contains 3 atoms. Ammonia contains 4 atoms. When you added up these, you get number of atoms. So largest number of atoms, therefore, should be ammonia, 4 atoms. Therefore, correct answer is C. That's how you describe Avogadro's law describing volume of gas samples and number of moles, number of molecules. I am outlining here gas laws we described in previous slides. Boyle's law, Gay-Lussac's law, combined gas law. And there's Avogadro's law. Somehow it's not showing up here. That's the ideal gas law. Once you have, let me see that I can get it. In between, there's a Avogadro's law. Avogadro's law is V1 divided by T1, N1 divided by N2. V1 divided by N1 is equal to V2 divided by N2. In the combined gas law, N is missing. After Avogadro's law, we have the idea this combined gas law included with combined gas law N, you get a constant equation. R is a gas constant, ideal gas law constant. This part is combined gas law. When you add the number of moles to an equation, you get ideal gas law equation. Therefore, it is clear ideal gas law is the ultimate gas law that describes in one equation property behavior of gases, including all variables, P, V, N, T, is equal to constant. Therefore, ideal gas law is very important. We're going to look into ideal gas law now. It is a culmination of all gas laws. Avogadro law, as I described previously, allows us to write a gas law that is valid not only for PVT, that's combined gas law, any mass, that means mass is number of moles that ideal gas law includes number of moles. This is the idea in ideal gas law. P times V divided by N times Kelvin temperature is equal to a gas constant. Constant now, ideal gas law constant. Normally this relationship, ideal gas law equation, is written in terms of PV is equal to nRT. When you rearrange the equation in terms of ideal gas constant, it becomes PV divided by N and Kelvin temperature. P is the pressure of the gas expressed in atmospheric pressure. V is the volume of the gas expressed in liters. N is the number of moles of gas. T is the Kelvin temperature. Therefore, in one equation, all four variables of gases are included. So notice, you don't have to have two values of P and V or T like in Boyle's law, Charles' law. Ideal gas constant is known. Therefore, if you are given volume, pressure, number of moles, or Kelvin temperature of any gas, you can do gas calculations directly. Ideal gas constant value is calculated using the fact 1 mole of, based on Avogadro's law. 1 mole of any gas at STP, temperature is 273 K. Pressure is 1 atmosphere. So knowing those values, you can plug into the ideal gas equation here. The P is the 1 atmosphere. Volume is the 22.4 liters. Moles, number of moles is 1. Kelvin temperature is 273. Therefore, it's easy to get the ideal gas law constant. Its units are liter atom divided by mole K. Sometimes we write liter atom, mole minus 1, K minus 1. You're going to see this is not clear. Mole minus 1, K minus 1. That liter atom ATM is atomic pressure. Units of ideal gas constant. Let's calculate ideal gas constant based on the data given for methane. Methane is the natural gas. 1 mole of methane, CHO, has volume of, that's the N, that's the volume, that's the pressure. What is the ideal gas temperature? What is the temperature? Ideal gas constant is given here, we calculate it. You solve the equation by plugging in these values found here. 1 atmospheric pressure, 1 mole of gas, ideal gas constant, and you get Kelvin temperature for methane, 244 Kelvin. That's how you do a calculation using ideal gas law. Like in other calculation using Boyle's law, Charles' law, you first identify the variables V, P, T, N, and calculate the unknown based on ideal gas law. Always use the ideal gas constant value. If the pressure is given in ATM, atmospheric pressure, the ideal gas value is constant value, ideal gas law constant is 0.0821. Now let's do a few problems. Okay, I'm going to do the calculation for ideal gas. What is the volume of 62.3 grams of nitrogen? Nitrogen is N2. STP value is, temperature is 273 Kelvin. Pressure is 1 atm. Ideal gas constant we calculated 0.0821. Knowing this from the problem, you can calculate. You write down the ideal gas equation and solve for volume. Solve for volume, you get this equation. Now nitrogen is N2. Formula mass of nitrogen is 17. 17 times 2 is 28. This is where you get the number of moles. We already talked about it. Number of moles is equal to grams divided by formula mass, given right here. Formula mass of nitrogen is 28. Therefore, N value is obtained here. Once you have N value, P value, V value, temperature value, and ideal gas constant, you can calculate the volume. This is after plugging into this equation. N is equal to 2.23. R is equal to 0.0821. Kelvin temperature is 273. And the pressure of the gas is 1 atmosphere. So you get 49.8, which is the B. Answer is B for that problem. Now, this is kind of a calculation you will expect when the number of moles are known or calculated from grams by dividing grams with formula mass, and you calculate any other variable, either V, P, or T. So in problem 75, the question is, what volume does 7.5 10 to the 20 molecules of oxygen? That's a volume question. What volume? Standard temperature and pressure is same, 273 Kelvin and 1 atm. So how do you get N? Number of molecules are related to N. If you are given certain number of, this is a large number, how do you get number of moles? A mole is 6.22, 10 to the 23 molecules of oxygen. Therefore, if you know number of molecules, this divided by this one, Avogadro's number, you get number of moles. Once you get number of moles, you can plug in the ideal gas equation, solve for volume. This is where I got number of moles. This is the number of molecules divided by Avogadro number. If you want to find, if you given certain number of atoms, if I ask you how many moles are in there, you just divide the number of atoms by Avogadro's number. Avogadro number contains, are the particles, number of particles contains in 1 mole of any substance, either atoms, ions, or whatever particles. So you get 0.0279 liters. Therefore, answer is C. That's how you do an ideal gas law calculation. Which of the following is correct unit for ideal gas law constant? We talked about it in a previous slide. Ideal gas law constant is, units of ideal gas law constant is liter atom divided by mole divided by Kelvin temperature, K. So this is not the Kelvin temperature is there, not there. Kelvin temperature is not there. This is Kelvin temperature divided by mole. This is the correct answer. This one don't have liter atom mole K. is multiplied by normally inverse. -1 means inverse, division by mole. Ideal gas constant, if you go back, units of ideal gas constant is liter, atom, mole -1, K -1. So that's the, if you look at the equation, that has to be on the bottom. That's our negative values here. That's the correct answer for problem 61. Correct answer is C. Calculate the volume occupied by 8 grams of oxygen. Now grams are given. You can calculate the moles. Oxygen is, formula mass of oxygen is 32. 16 times oxygen is, molecular oxygen is O2. Formula mass of O2 is 32. So I calculated the formula mass of oxygen here. It turned out to be, when you calculate the number of moles, it turned out to be 0.25. Now you solve for V just like in the previous example. So V is, after plugging moles, ideal gas constant, temperature, and pressure, you get 5.6. That's the answer A here. That's how you do an ideal gas law calculation. That's another problem. Now here, 7 grams. Nitrogen is N2. Formula mass of nitrogen is 28. 17 times 2. There are 2 nitrogen atoms. Therefore, number of moles is grams divided by formula mass. 7 is the number of grams right here, and divided by formula weight right here, you get 0.25 moles of nitrogen. Then you solve for, the question is not volume, pressure of the sample. You rearrange the ideal gas equation, solve for P, and plug in the values given here. Celsius value need to be converted. It's already converted for you. You added 273 to 10, you get 283. So these values are plugged in the equation right here. And you get 2.32 atm of pressure. B is the correct answer. This one, right here. Which of the following are measurement of standard temperature and pressure? We already talked about standard temperature is 0 degrees Celsius and 1 atmospheric pressure. This is not Fahrenheit, not Kelvin. Therefore, only one answer. Correct answer is choice A. 0 degrees Celsius, 1 atmospheric pressure. It could be 273 K, same as 0 degrees Celsius, or 762. Both are standard temperature and pressure. Now we're going to go to Dalton's law of partial pressure. Dalton's law of partial pressure is used to calculate total pressure P big T of a mixture of gases when the sum of the partial pressures of the component, each individual gas is known. Now, this idea about partial pressure, this is the total pressure. Partial pressure is defined as, for example, I have a problem here. A tank contains nitrogen, oxygen, and carbon dioxide. There are three components. This is the partial pressure of nitrogen, partial pressure of oxygen, and partial pressure of carbon dioxide is not given. The total pressure is given. How do you calculate the partial pressure of carbon dioxide? Total is 4.6. Other two components adds up to 3.0 here. These two add up to 3.0. Therefore, 3 subtracted 4.6. That's the carbon dioxide. That's how you calculate unknown partial pressure of a component in a gaseous mixture. Now let me tell you about partial pressure. What exactly is partial pressure? Partial pressure is pressure exerted by each component. For example, nitrogen, oxygen, carbon dioxide. This is a gaseous sample. Gaseous samples are different from liquid solid samples. Gaseous samples are particles of the gases are so far away from each other, they wouldn't know the presence of other components. So if you put oxygen alone in the same container, same number of oxygen, that's the pressure exerted by oxygen or nitrogen component. Is called a partial of that component. Therefore, total pressure adds up to total pressure is obtained by adding up component partial pressures. That's the Dalton's law of partial pressure. Let's do a problem. A reaction vessel has total pressure of that. The partial pressures of nitrogen is, what is the partial water vapor? This is water vapor. That's H2O nitrogen. This is a mixture of nitrogen and water. Water vapor is H2O. Therefore, the total pressure subtracted nitrogen pressure would give water vapor pressure. This is the total pressure. This is the nitrogen partial pressure. Therefore, it gives water's partial pressure. That's how you do a calculation, knowing the total pressure and unknown partial pressure. If you know partial pressure of other components. Similar question. Here you have carbon dioxide and water. The total pressure is this, 2.502. Carbon dioxide has this pressure. What is the pressure of water? So it's similar question to the previous one. The total is this subtracted the partial pressure of carbon dioxide. That's the P total. You get the P partial of water. That's choice A. Now it's pretty simple to calculate partial pressures or total pressures using the Dalton's law of partial pressure. Now you have a sample of gas containing 4 components: helium, neon, argon, and mercury. Not mercury, xenon. Helium, neon, argon, and xenon. Each partial pressure of each component is given. Now you ask in total pressure. So total pressure is sum of the partials. Total is equal to partial. That is basically the Dalton's law of partial pressure. You get 777, which is the answer here. That's how you calculate P total from P partial. Now, this is a problem similar to the first two problems, 133 and 134. Now, the total pressure is given. If the total pressure is this, one of the partials are unknown. Unknown is neon. Argon is known, helium is known, partial pressures, and the xenon is known. Therefore, total subtracted known partial pressures of helium, this is the helium, this is the argon, and xenon. You calculate the neon partial here. So when you calculate it, you get the value 366, which is the choice C. The partial pressure is argon gas mixture, argon and oxide gas mixture, and nitric oxide, argon and nitric oxide. Now this is not a calculation, it's a concept question. If you look into problems, the partial pressure is definition of partial pressure. I was trying to explain it. Argon would exit absence of nitric oxide. That's the correct statement. The partial pressure is the pressure exerted by a component when that component is alone in the container. Normally they are independently added to produce the total pressure. That's the correct statement. The statement B, the percentage has nothing to do with partial pressure or molar mass here right now, equal to total pressure divided number of argon atoms. These are all a statement which doesn't make sense. First one is the correct statement of Dalton's law of partial pressure. Now we finish all gas laws. We gone over Boyle's law, Charles law, Gale-Sachs law, Avogadro's law, ideal gas law, and Dalton law of partial pressure. There are 6 equations we use based on these 6 gas laws. You have to kind of go through and do the problems and get familiar identifying problems to a particular gas law. Now we're going to change the topic. We're going to look into properties of gases, liquid, and solids. How we describe their properties in terms of the molecular theory, kinetic molecular theory. Kinetic molecular theory for matter is similar to Dalton's law of Dalton's atomic theory. It's similar to Dalton's atomic theory. Kinetic molecular theory have assumption, just like Dalton atomic theory had four assumptions. All atoms of matter is composed of particles called atoms. That's how we describe the Dalton's atomic theory. Kinetic molecular theory starts similar way. Assumption of kinetic molecular theories. Gases. This is for gases. Kinetic molecular theory is different for liquids and solids. We're going to talk about it a little later. Gases consist of particles constantly moving through the space in random direction with various speed. So gases are constantly moving, unlike liquids and solids. The kinetic molecular theories are ideal picture. Kinetic molecular theory assumes there are no attractive forces between gas particles. The average kinetic energy of gas particles is proportional to the Kelvin temperature. It describes motion of particles in a gas is due to increase in velocity. Kinetic energy is half mass velocity squared. We go nowhere. Kinetic energy is half times mass velocity squared. So therefore, kinetic energy increase, velocity increase. When a gas is heated up, it increases the velocity of the particles, also kinetic energy. Kinetic energy of gases is directly proportional to Kelvin. When you heat up a gas, the kinetic energy or the velocity of the gases increase. Kinetic energy is directly proportional to Kelvin temperature. In a gas sample, molecules collide with each other. The collisions are elastic. That means they don't stick to each other. Elastic means this. They exchange kinetic energy. However, kinetic energy may remain the same among the molecule particles of the gas. On the average, kinetic energy is same, but different particles have different kinetic energies. It's just like cars on a highway. They are not same velocity, kinetic energy. Gas particle has no volume. Kinetic molecular theory assumes that gas has no volume. This is true because compared to the volume of the container, gas volume is very small. Therefore, when you're dealing with gases, it seems to not affect the properties of gas. Volume of gas is very small. Therefore, all gas particles, regardless of their size, behave same. The last assumption, number 6, define the pressure of a gas. Pressure is due to the collisions of particles on the wall of container. The pressure is defined as force per unit area of the wall of the container. That's how we define the pressure. Collision casts the pressure on the wall of the container for gases. Now, as I said before, kinetic theory is an ideal description of gases. Let's look at how real gases behave against ideal gases. The 6 assumptions of the kinetic molecular theory we described in the previous slide. It's an idealized picture. And their interactions are idealized also. There's no attractions. There's no volume for gases, ideal gases. The atoms, unlike ideal gases, real gases do occupy some volume. If you have oxygen and ozone, O3, this has certain number, this is bigger. Real gases have volumes, different volumes. But for our ideal gas laws, all these gas laws are describing ideal gases. The volume doesn't matter. Volume of a gaseous particle doesn't matter. But real gases doesn't behave. They don't have same volume. They have some volume. At STP, standard temperature and pressure, most real gases behave same way as ideal gas predicted by kinetic molecular theory. STP is around 0 and 1 atmosphere pressure. Most of the lab work we do about gases, experiment we do on gases are done at around 0 degree. Therefore, they follow ideal gas behavior. There are forces of attraction between particles of real gases. Atoms or particles could be atoms or molecules. So real gases have attraction. Ideal gases have no attraction. We're going to see how it affects in the next slide. In reality, no gas is ideal. They have volume, they have attraction in between particles. We're going to look into attraction between particles in gas phase, in liquids and solids. There are intermolecular forces between particles which are cohesive in nature. These attractions are electrostatic. They are called cohesive forces. They tend to bring the molecule particles of gases to form liquids and solids. When a gas sample is cooled, it becomes liquid, then it becomes solid. Because of the cohesive forces predominate, they become more forceful. When the temperature is higher, that means you're heating matter, sample of matter. Disruptive forces are kinetic energy, velocity, tend to move away the particle of matter. Therefore, they tend to break up the cohesive forces coming from intermolecular forces between particles of matter. At near standard temperature and pressure, the cohesive forces of attraction between cohesive forces are intermolecular forces attracting particles of most gases are small. They can be ignored. According to kinetic molecular theory, intermolecular forces are not there in gases, but in real gases, they do have intermolecular forces. At or near STP, cohesive forces of attraction between gases are there, but they can be ignored. When the temperature is not at STP, when the temperature decreases and pressure increases, if you cool gases, ideal gases, or compress, P increase means compress, or both happens, kinetic or disruptive forces decreases. As the temperature goes down, pressure increase, the force of attraction become important. Attractive cohesive forces become important. Then gases condense to liquid. Solid, ultimately liquid solidify, liquid becomes solid. According to kinetic molecular theory of gases, gases will never condense to liquids. Why? They are assumed to be no intermolecular forces. But if you increase the temperature beyond standard temperature and pressures, decrease the temperature or increase the pressure, they tend to become real gases, and gases become liquids and finally become solid. In order to understand the properties of liquid and solid, we must look at the nature of the intermolecular forces of attraction. To describe why we have condensed phases, that means liquid and solid, where the particles are so close, we have to look into intermolecular forces. Now we're going to talk more about intermolecular forces to describe the properties of liquids and solids. Let's answer a few questions. Which of the following is not true of the kinetic molecular theory? Gas molecule has no volume. Kinetic molecular theory, one of the assumptions is gas particles. Gas particles mean molecules of gases. That's true. Gas pressure is caused by collision between gas molecules and the container. That's true. That's the definition of pressure. When the gas molecules collide, they stick together. No. Collisions are elastic. They bounce off Therefore, kinetic energy is conserved. They exchange the kinetic energy during the collision, but they move at different speed. That's not true. I'm sorry, I put they don't stay. None of all these are true. That B is also correct. They're asking for not true. This is true. Not true is C. I got confused. They are looking for true answer. Not true answer is C. Which of the following statement is not part of kinetic molecular theory? Matter is composed of particles that are in constant form. That's correct. Therefore, that is not part. There's a part of particles velocity increases. That's part of the. We are asking question, not part of. Particles in a system cannot transfer energy. The collision, like we described here, they transfer energy. This is not a part of kinetic molecular theory. Particle of interaction involve electrostatic attraction and repulsion. Particle interaction involve particles don't interact. Therefore, that's not part of it. Answer is C. In which of the following grouping of terms are the three terms closely related? Now listen carefully. This is important. There are three groupings in terms of cohesive forces and disruptive forces. This group is kinetic energy is disruptive. Energy of motion is kinetic energy, disruptive. This doesn't belong here. This is disruptive. This is cohesive. Therefore, three terms are closely related. These first two terms are related, but not the last one. Potential energy is attractions, energy of attraction. Attractions are not disruptive forces. Therefore, this doesn't belong here. These two go together, first two. Kinetic energy is disruptive. Electrostatic attraction is cohesive. Interaction between particles are electrostatic, that cohesive. This doesn't go together with these two. Disruptive, kinetic energy is disruptive, but the electrostatic attractions are cohesive. Now all three have to be same. Potential energy is attractive. Electrostatic interactions are attractive, cohesive forces. Therefore, the last choice, D, describe the inner molecular forces, which are cohesive forces, electrostatic in nature, and needs a potential energy. D is the correct answer. Let's look into last slide here. Intermolecular forces in liquid and solid. We discussed three types of intermolecular forces. We are going to discuss three types of intermolecular. Their origin are electrostatic. That is, attraction between positive and negative charges of the molecules. There are polar molecules. Interaction between positive and negative parts of the polar molecule is the origin of intermolecular forces. If you look at the forces between atoms, first force is direct bonding. It's called interatonic atomic forces. We talked about this ionic bond and covalent bonds. The last, these are covalent bonds. They are stronger bonds. They are not intermolecular forces. They are interatomic. We don't, attraction between particles in a gas phase or liquid and solid phases are weaker. 3 types of intermolecular forces are described at the bottom. This is the intermolecular forces. There are three hydrogen bonding, dipole interaction, and the London dispersion forces. The first 2 are found in polar molecules. These 2, dipole and hydrogen bonding, are found in polar molecules. Remember we talked about polar molecules? Water has polarity. They attract, positive and negative ends attract. Therefore, dipoles attract in both cases. In here also dipoles attract. What is the difference between hydrogen bonding and dipole interaction? Hydrogen bonding is special case of oxygen, fluorine, hydrogen, OH, NH, dipoles are strongest. So when a dipole is formed between nitrogen and hydrogen, they are so strong. They show hydrogen bonding. We're going to talk about this little later. Okay, I'm going to stop the class for today. You guys go back and go through the slides again. If anything you didn't understand, go away and go over the slides until you get them. Okay? I'm going to see you next week. Are you guys there? I'm going to stop the class.
You have a good one.
Yeah, you too.
You have a nice day, sir.
Thank you. You too.
You too.